it would be very, very dangerous to you. Luckily, the Earth, because it has an iron and nickel core surrounded by a molten iron and nickel mantle, that spinning molten metal creates a magnetic field for reasons that you can learn if you take physics. I'm not going to go into it now, but there's a magnetic field surrounding the Earth. So those charged particles are zooming in from the sun and they bounce off the magnetic field. Bounce, 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 which is great. But sometimes they bounce at just such an angle that some of them will glance through our atmosphere. Those charged particles are carrying a lot of energy. They'll glance through our atmosphere, charge up atoms in our upper atmosphere, and just like the plasmas that's being produced here, those charged particles will have their electrons jump up and then come back down. And when they come back down, they give off photons, which we see. So that's where it comes from. So the Earth's magnetosphere directs most of the particles away. Some of those charged particles glance our atmosphere and excite gases in our atmosphere, and it is those excited gases that we see, and we call that the aurora borealis. Now, there will be no aurora borealis on Mars until we create an atmosphere around Mars, but even when we do, you're not going to be able to go sunbathe on Mars. You can go outside with very little clothes and sunbathe and still be mostly okay. The UV, the ultraviolet, will get through, but the charged particles that will kill you very quickly won't, because the Earth has a magnetic sphere, or magnetosphere, a magnetic field. Mars doesn't have that. Mars is a solid rock block, and it doesn't have a magnetosphere, so even if we did colonize Mars, you couldn't go sunbathe on Mars because the charged particles would hurt you very, very bad. Question?
So if we didn't have a magnetosphere, then we'd all die?
Correct. We'd starve, because the plants would die first. We could basically, all we'd have to do is run out with an umbrella, and we'd be okay.
We wouldn't die because life wouldn't start if there wasn't a magnetosphere.
Yeah, exactly. We wouldn't have been around. But if our magnetosphere suddenly disappeared, we'd all be like, you should go outside with an umbrella because it's a sunny day. Even if it wasn't a sunny day, go out with an umbrella made out of aluminum or mylar. But yeah, the plants would all die. We wouldn't be able to make any food.
Make them inside.
Make it inside. Yeah, maybe we could. We could probably support life for maybe 100,000 people. Who would those be? Okay. Anyway, all light. Back to our light. All light travels at 3 times 10 to the 8th meters per second. It's such an important number, the speed of light, that we give it a letter. C.
Is the answer.
Everything travels at c. C is equal to lambda f. And c is 3 times 10 to the 8th meters per second. Everything travels that fast. Light, radio, microwave, infrared, ultraviolet, this tiny little slice of visible light. Gamma rays, cosmic rays, X-rays, they're all traveling that fast. Yeah?
So, because waves usually change speed when they go through like different mediums, does that affect light too, or is it just like so small that it doesn't matter?
Both. Light does change speed when it goes through mediums, and that effect is called the index of refraction of the material. It is considerable enough that we can notice it, but mathematically it's very, very small, a very, very small difference. You're still talking about times 10 to the 8th meters per second. But it might not be 3, it might be like 2.9 times 10 to the 8th meters per second. So when you open your car door and you see those heat waves come out of your car, that's the index of refraction. Hot air has a lower index of refraction than cold air, so it kind of, you can see the waves move, the light basically bends between those two things, and that's what you see. Okay, C equals lambda F. So all waves carry energy, and that energy is based upon only one of those variables. It's based upon frequency. Okay. By the way, you don't need to memorize this, but it is kind of a handy thing to know that there's visible light right there. Guys, do I need to move you to? No. Okay. There's visible light right there. Infrared literally means below red. Then microwaves, radio waves, this is all radio waves. And then slightly higher than we can see is ultraviolet. And then X-rays and gamma rays. This is the electromagnetic spectrum. We can detect a tiny little slice of it, itty bitty slice. Some insects can see into the ultraviolet and the infrared. Some birds can see into the ultraviolet and infrared. We cannot. Okay, so in summary, all electromagnetic waves move at the same rate. They move at 3 times 10 to the 8th meters per second. A blue wave that has higher frequency will be carrying higher energy. A red wave with a lower frequency will carry lower energy. And there's your important formulas. These two.
What's that symbol?
Now, we can actually calculate how much energy a photon is carrying by a constant named after Maxwell Planck. Planck. He did some pretty awesome stuff in tying electricity to magnetism and electricity to light. In fact, there's a whole set of equations that you're going to learn if you take electrical engineering and more advanced physics classes called Planck's equations. They all require calculus, so we're not going to go into them here. But the important thing is the energy varies with frequency. And the speed of all electromagnetic waves is the same. The wavelength is inversely proportional to the frequency if the constant proportionality is speed. And this is Planck's constant. We'll have Alexa read it to you. Alexa, what is Planck's constant?
Planck's constant is usually defined as the constant of proportionality relating the energy of a photon to its frequency, approximately 6.626 by 10 to the power of minus 34 joules second.
I love Alexa. Thank you. Okay, so, yeah, 6.63 times 10 to the negative 34 joule seconds. So, are there any questions before I do some examples? We're going to end the class doing some examples. You're going to need a calculation device as well. So, a calculadora. Yes?
What is the top for the not C equals
3 times 10 to the 8th meters per second, and C equals lambda F.
question. What is that scorpion? What's that scorpion?
Oh, this
Yeah.
varies with. Yeah, this means lambda varies with the inverse of frequency. Energy varies with frequency. So it's not equal to, it means varies with. Okay, let's do some examples. How fast is an X-ray with a wavelength of 3.2 nanometers? First of all, nano is 10 to the negative 9. So, how fast is an X-ray with a wavelength of 3.2 times 10 to the negative 9 meters? If you're punching on your calculator, you're doing it wrong. If you're looking for a formula, you're doing it wrong. How fast is an X-ray?
Oh. Yeah, 10 to the 19.
Yeah, the answer is 3 times 10 to the 8th meters per second. But don't we have to? No. If you know it's an X-ray, some kind of light, it's going to be traveling at a speed of 3 times 10 to the 8th meters per second. Give me a thumbs up if that makes sense to you. This is pretty important. Now, the next thing you're going to have to calculate. Now, what is the wavelength of a radio wave with a frequency of 2.3 times 10 to the 9th hertz? To do that, you realize that C equals lambda F. C is 3 times 10 to the 8th meters per second. You are looking for wavelength, so look for lambda. And the frequency is 2.3 times 10 to the 9th hertz. Solve for lambda. Question?
Are there any like conversions that go in between like hertz and meters per second and all that stuff, or is it just kind of?
No, it's just that. C, that's a good question though. C is the units of meter per second,
Yeah.
and wavelength is meters, and frequency is per second, 1 over S. So
Okay.
they just, yeah.
Okay.
As long as you're using standard units, you're going to be happy. Now the metrics with the nano and stuff, that's kind of important. We'll talk more about that in a little bit.
What's the like unit for wavelength?
Meters. Yeah. Because it is a length. You have that. Okay, so you're dividing a 10 to the 8th by a 10 to the 9th. So hopefully your number is going to be itty bitty. What is the wavelength? 1.3?
No,
0.13, that's what I meant.
0.13?
Yeah.
Yes.
0.13. That sounds about right, because 10 to the 8th divided by 10 to the 9th should be about a 10. Okay. So 0.13 meters. How big is that? That is a radio wave. That is that big. That's how big the radio wave is.
I thought that would be like almost so small.
Now, there's some elaborate physics that goes into making radio waves, and we can actually fold this on itself 4 times. So the antenna that makes the radio waves can be reduced to about 1/4 that, which is about that big. That is the smallest a cell phone can be made, because the antenna has to be that big.
How big my cell phone should be?
Usually the antenna is inside. Old cell phones you had to flip up and then pull the antenna, but we don't have to do that anymore. We used a little bit of more elaborate physics, so we don't have to do that. Okay guys, 2 more minutes. Here's another one. What is the frequency of a 500 nanometer green laser? Okay, again, nano is 10 to the negative 9. So this is 500 times 10 to the negative 9 meters. So you set your equation once again, 3 times 10 to the 8th equals, in this case, 500 times 10 to the negative 9 multiplied by frequency. It's a big number. If you are using your EE key properly, you will get it right. If you're using your EE key improperly or not using it at all, you will get it wrong. I want you to get it right. I'm rooting for you.
What does that say that after the negative 9 it says some math?
Times frequency. So that is the variable you're solving for, times frequency.
Wait, is this one for today? Because it says prior to test day.
As in like right now.
It is like today?
As in like right now,
Oh,
yeah.
okay.
So once you finish this exercise, you need to go to your counseling office.
It's weird though because test day is Wednesday. Yeah, test day is Wednesday.
Right. They want you to do the paperwork first. Oh. That way you don't have 200 people are like, how do I bubble this in? Okay, do you have an answer?
Yeah. 6 times 10 to the 14.
Yes. 6 times 10 to the 14th. And the unit is hertz. And I end with these questions. To solve for energy, we're going to be doing this in, quite a bit when people are leaving. So to solve for energy, you just take your frequency here and you multiply it by Planck's constant. So energy equals HF, which is 6.63 times 10 to the negative 34 multiplied by that. That'll give you the energy. And to end, of ultraviolet and infrared, which one has a larger wavelength?
Infrared.
Ultraviolet. No. Infrared. Why do you say that? Red. So red has a larger wavelength. Blue has a higher frequency. Which one's traveling through light or through the space fastest? Blue. They are the same. What about nasty, nasty gamma rays? Them too?
Yes.
Them too.
How do you spell Planck?